My name is Roberto Tyley, and I work for The Guardian, where we break stories like this. Frequently. Somehow the NSA and GCHQ are just exceeding everyone's expectations on that front. And so we actually do a lot of Scala at The Guardian. One thing I recommend you guys check out is our front end, which is written entirely in Scala as a series of play apps, and it's open source under the Apache v2 license. So if you'd like to see us developing the open, you can go there to Guardian/frontend, and you can see us developing the open 100 commits a day, and deploying quite a few times a day as well. So we use a lot of Scala, we use a lot of Git, we got hundreds of Git repos. And so the title of this talk is Git Going Faster with Scala, which prompts the question, how? And then actually it prompts the question, what? Because I have to confess that there's a pun in the title. It's I don't know if there's any non-English speakers here, but a pun is like a crappy joke. And so my talk has a crappy joke in its title, and it's got two meanings. One is the performance meaning, Git going faster, actually the source control system performing faster with Scala. And the other one is just like, let's get started with this idea, let's prototype this thing. We're like in the kind of Git going faster kind of, that was a Welsh accent. That's a Welsh accent. Anyway, moving on. So that's the two themes of my talk, is doing those two things. Faster prototyping and faster performance. And you know, if you love Scala as much as me, you probably kind of expect the prototyping one maybe, but the performance one, perhaps that's a surprise that Scala can outpace Git. So in order to tell you about how this can be, I'm going to tell you about a tool I wrote called the BFG. And in order to tell you about the tool, I need to explain the problem. And the problem is basically people check dumb shit into repos, and they check in passwords and credentials and massive files, and this is like, it's just human. People make mistakes, but source control is not very forgiving because it always remembers your mistakes, and they come back to haunt you. So you get all of these things lurking around in your history, and you're like, oh, now I can't share this repo with this person because it has my passwords in, or I can't share this repo because it's like a 2 gigabyte download for a few video files that I once checked in and I deleted later, but are still in the history. So, in fact, big is perhaps smaller than you might expect. In GitHub, like, they will warn you if you try and upload a 50 megabyte file, and they will just flat out deny it. As of a year ago, they will just deny you uploading anything bigger than 100 megabytes. So a lot of people found themselves unable to push to their Git repos back in June 2013. And on the scale of little Android clients for Git, I actually wrote one called Agit. Mobile device is pretty limited, and so I get really upset if anyone puts in more than like a 5 megabyte binary file into a repo, because Agit just like falls over and it just can't decompress that data, which is a requirement of the way Git works. So people have this problem, and then they go to Stack Overflow, and they sort of come and worship at this monolith, like, you know, monkeys, basically. So how do we remove this shit from Git? And they don't know how. It's like incredibly obscure. What they eventually get led to is git-filter-branch, which is an amazing and powerful tool. It's got lots of options and can do lots of things, and you can rewrite your history completely with this tool. But there are some problems with git-filter-branch, like just from a user's point of view, never mind the implementation. It's difficult to use. Like several of these incantations down here, you've got to have those in, and you've got to have them in just right. Otherwise, it won't do what you think. You won't actually get rid of all the nonsense you're trying to get rid of. So it's difficult to use. It's also quite slow. So, you know, as a Scala developer, we're all like Scala developers, right? We're all like, oh, maybe I can rewrite it in Scala. And you think, oh, this would be fun. I'll rewrite it in Scala. So is that like even possible? Well, there's a very nice JVM-based version of Git called JGit that's kind of sponsored by Google and several other companies. And performance-wise, like, this is very depressing. I wouldn't actually read this because it's very depressing. It talks about how slow Java is. This is from the lead developer of JGit, Sean Pierce. And he basically says, oh, Java can't do this, and it can't do that, and JGit is slow because of these things. And it's quite depressing reading as a JVM-based developer. So you just avoid looking directly at this posting. But the good news is that was back in 2009, and things got better. So by 2011, like Google's pouring resources, everyone's pouring resources, and they used JGit to serve the source code of Ice Cream Sandwich, the version 4 of Android, when it came out. And in the first 24 hours, JGit served 36 terabytes of data. So that's pretty good going. And it also was released on mobile phones. That's my little Android Git client there. I was really pleased with that. So even on constrained devices like JGit could work, because Android obviously supports Java. And then in 2014, hey, it's even better because vanilla Git, the C Git, is actually borrowing performance features from JGit. So JGit's actually kind of ahead in innovation. So that's nice. And so where you end up is, okay, JGit, I can write Git stuff on the JVM with performance that's kind of comparable to CGit, sometimes a bit slower, sometimes a bit better. It's kind of comparable. So that's cool. And all right, so like rewriting git-filter-branch in Scala, okay, that's pretty cool. And you know, we can sort of experiment. Like I walked in late on Monday, and some guy was talking about how you can start prototyping really easily with Scala, and he's like, you can start with a one-liner and you can grow, and he's absolutely right. Whoever this guy is, he's completely right. You can experiment with Scala, but you've got the full power of that language to grow. So you can start prototyping, create tiny little Git commands. That's great, and test out ideas and stuff. And you can move on to more exciting and fully fledged things, and you never have to leave your nice sort of JVM-based world if you don't want to. But the problem is, right, okay, right, so I could rewrite git-filter-branch in Scala, and that's kind of cool, and I could, you know, dress things up a little bit with implicits and things. But the problem is that git-filter-branch, it is difficult to use and it's slow, but it's really slow. It's like, you know, overnight job slow. It's 24 hours slow to rewrite your Git history. And so if you just try and re-implement git-filter-branch, you're going to be as boringly slow as that, and that's not very interesting. So I do a lot of hacking on the tube. That's like my day job is at The Guardian, and I work on Scala there, but my hacking I do on the tube and on journeys. And what I needed was an idea. I needed an idea to do something that was altogether different. And so I was noodling around with Scala, and I was with my wife and my little tiny baby daughter girl. She was about maybe a year old. And so we're all heading up north to go and visit some, like, you know, important relatives, and we all have to be smart and tidy. But then I get an idea, and I'm like, to my wife, I say, is it all right if I just completely ignore the rampaging small child and just hack for like half an hour as we cross London from one side to the other? And my wife is a wonderful person, so she's like, yeah, okay, I'll take care of the child. Who's, you know, needs to be fed, and, you know, actually, she's really lovely. Rose is a great girl. I didn't say anything bad about her. And this is the idea. This is the thing. Git-filter-branch lets you do anything to a Git repository. But for us, we're just removing unwanted data. We don't want to do anything. This is too much power at too great a price. So who here, like, fully understands the Git object model? Hey, that's brilliant. Okay, right. So in that case, I'm going to switch now to explaining the Git object model, because to understand the speed benefit, you've got to kind of understand that. So in Git's kind of like it's like a key value store. It's simply points from object IDs to objects. And so the objects might be commits, they might be files, they might be directories, like a little text line-by-line representation of a directory saying this is a file, this is a folder. And yeah, so those are the three main object types in Git, and commits and trees are basically just like text files listing out what's inside them. This is the commit message, and blobs, they're just represented as basically the raw binary data. So if you type into a file, then basically what happens is a little Git header gets stuck on the top, and then with all Git objects, they're just hashed using the SHA hashing algorithm, and that becomes the Git ID. So that ridiculously long 40-character string that specifies your Git ID, that's basically just a hash of the content of what it is. And so you'll have seen hashes of commits, but files have hashes as well. So any individual file will have a hash, and also the directories have a hash. And they're all stored once in Git. So let me just show you. So I've got the source code for .e checked out here. .e is the new Scala compiler. Oops. dotty.git. So if we have a quick look at the log, let's have a look at like some of the initial commits. So that commit there, if I just print out what this looks like, the raw object for that commit, bomb. Right, so this is it. This is the text of that. That's the object that's stored, and if you hash it, you'll get that hash. So yeah, it's fairly simple. It says the file tree that this commit relates to, this complete snapshot of the file tree, is this file tree, and that's the previous commit, as you can see there. This is who wrote it. Again, it's that guy who was doing something the other day, and his initial commit. That's actually his second commit. And so we can say, okay, right, let me have a look at that tree object then. What does the tree object look like? And it looks just like a series of lines, set of lines of text. This is all that's going on in Git, is it's saying, okay, I've got a folder, which is called tree, called .worksheet. Looks like Martin checked in his worksheet folder. And it's got a blob, the file, the README file, and it's got another folder there. And so we can do this all the way down. We can follow this tree, this graph all the way down, and we can see what each object is. I could cat the README file, though obviously it's probably a bit big. Oh, right. Yeah, so it's a pretty short README file. So and that's all Git is a key value store where you've got hash IDs, and you can look them up nice and quickly to get out the Git object. And from this you can say, okay, this commit has this full file tree, and the file tree is all of these subfolders. And for instance, if something doesn't change, it doesn't get stored more than once because it always has the same hash, right? There's no change in this information inside it, so then the hash won't change. So if you have, like, supposing that, yeah, in this subsequent commit up here, Martin has deleted his worksheets folder, right, because he realized he shouldn't have checked it in. But that means he won't have touched this source folder down here. So if we have a look at the content of this, whoops, daisy. Yeah, if we have a look at the content of this commit and have a look at its tree, actually. Oops, a daisy. Oh, no. Right, fine. I'll type it up manually. I must have typed that wrong. Oh, wait a second. I should probably make this bigger for you, shouldn't I? Sorry about that. Terminal. That's fractionally bigger. There we go. Right, so yeah, let's have a look at that tree. Okay, and if we compare that with the parent commits tree, sorry, all of these hash IDs look kind of intimidating, but they're just hashes. So if I then look at the tree of that commit, so you can see that the source folder in the previous commit had this hash ID, and then later on, once Martin had deleted the worksheets, which were up there, then the source folder was still the same. There was no changes, so it was only stored once. And so that means they're kind of shared across all your commits. So perhaps that was kind of a rather viciously command line based way of showing you. So I'm going to show you a shiny thing instead. Who wants shiny things? Shiny thing. Yay, shiny things. Come on. Shiny things. Woo! So here we are. We are looking at the source code of the Dotty compiler in 3D. And so as I go forwards like that, I'm going into the past of the project to the very start when it's small. And as I go back, we're looking at, there are more files, there's more stuff going on. So, oh yeah, so let me just show you, for instance, let's highlight this README file. There you go. So I just highlighted that file in blue. And you can see, right, so we're looking at the history side on now, okay? So as maybe this perspective isn't great, but on this side, that's the past. On this side over here, this is the future. And as we slice this sausage, basically it looks like a sausage. We're in Germany, everyone likes sausages. Yeah, so it looks a bit like well, not really like a sausage, but it looks a bit like a sausage. As we slice the sausage, that's a commit. So the files are laid out in kind of like this radial directory structure. And so you can see that this file that I've highlighted, the README file, occurs in many places in the history, and that's the hash ID. The hash ID is represented, is stored precisely once, but is used lots of times in the history because the file didn't change. Nobody bothered to update the README file. So if I was to tootle along here for a bit, sorry, it looks a bit like Star Wars, doesn't it? Except maybe on the 1970s low-budget version. Yeah. So what eventually happens is that someone updates the README file, and then the blue runs out. Yeah, there you go. So just here, that's when someone actually decided to update the README file. So there's the thing. What's git-filter-branch doing? Git-filter-branch is going through history, and it's letting you run a command against each commit in history. So if I just animate what git-filter-branch is doing, it looks a bit like this. Okay, so it's going commit at a time, commit at a time, commit at a time, and each time it hits a commit, it runs your little bash script. And your bash script has to do this work of trying to figure out how to clean up history and how to remove the big file. And then the bash script ends, then it moves on to the next commit. So it's doing, I don't know, like a few commits a second here. This isn't actually instrumented off a real filter branch session, but it's what it in principle does. So, and what you'll find is that filter branch kind of goes okay until you sort of start getting large amounts of files, and then it starts to slow down, gets really sluggish, it's really boring. So if you think about that, that's ridiculous, because we have files that are stored precisely once. Let's just clean them once. Let's not clean them repeatedly over and over again. The files are stored. The files are represented like 500 commits. Cleaning them 500 times is ridiculous. So, for our use case, git-filter-branch gives us way too much power, more power than we need. So that's why it's too much power, because it's letting us clean the same object lots of different ways. But all we care about when we have rotten passwords or big files, we don't care where it is or when in history it is. We just want it gone. So this is what git-filter-branch is used for a lot of the time. Maybe occasionally for other things, but mainly just for this. So there's this thing. Item of content in Git is stored exactly once. Let's just clean it once. And all we need is a very simple map from dirty object ID to clean object ID. And what I mean by that is, if I give you the Git ID of a file, I just need to be able to map to what that file would look like if it was clean. And if I give you a tree, a folder, then you can just give me what that folder looks like once it's been cleaned. So for any given snapshot of a folder, say a folder that doesn't change very much, you only ever have to clean it once. And so this map is it's growing with concurrent updates, because we can do this kind of stuff concurrently in a dynamic programming memoization kind of file, kind of way. But it's otherwise immutable. So like once you've cleaned something, you never have to figure out how to clean it again. So that's what the BFG does. So I was on the tube and with my crazy, wonderful daughter running around, and I think this is brilliant. Like, this has got to go faster, right? So I'm coding it up on the tube, and I've got the time it takes to go from one side of London to the other to figure out if it works or not. And just like at the Scala REPL, I'm typing out these commands, these JGit commands, and I'm trying them out. And just as we pull into our final destination, which was Highgate as it happens, the doors open, my run completes, and it's in like a fraction of a minute or something. I'm like, this is amazing. It's like 100 times faster. and the doors open, and my daughter's nappy explodes everywhere. There is shit everywhere, and she's completely like soaked in like awful stuff. And we have to strip her down on the platform and like borrow like clothes from passers-by. And people actually do like lend clothes. Isn't that nice that in London, like one of the nastiest cities in the world, that people just like lend you clothes and like say, yeah, you can send us back to it later. So I thought it was really nice. So that was the sort of start of the BFG tool. It was started off on a single, pretty high stakes underground trip to Highgate, and that's a pretty good prototyping session, even if it does end with an exploding nappy. So that was a prototype where I demonstrated that the concept works pretty well, and from there I was able to take the idea and sort of scale up, because we can apply all the wonderful things of Scala, and we don't need to grow into some other place. I could have tried to do this with Bash. It would have been hellish. And at some point you would have wanted to do something like in C or something like that. But this was way more fun. And also Git, turns out, runs pretty damn fast on the JVM. So once you've been using Scala, of course, you can do fun things like, so the JGit API is written for performance. That's what really Google cares about. And it's not that much fun to use a lot of the time, because they've had to optimize for performance. For instance, there's this thing called a tree walk that walks over all the files in a given commit. And it's like kind of like an iterator, but it's not really. It doesn't have the right interface. But then you can just dress it up with a nice implicit class, and then you can do for comprehensions on it, and it's much more fun to work with. So that's the BFG Repo-Cleaner, and so the question is then, there's a bit of code, because it's a Scala conference, I should probably show you some code. So we just memorize these functions. It's using like concurrent hash map for the map, and I'm not sure if there's a better data structure out there. If anyone knows of a better sort of immutable growing map structure, I'd like to know. So there's the cleaning operation. Just says from one object ID to another. Open up the object, find out the type, and then we'll do like a cleaning operation by type. So we don't actually clean blobs, we clean trees, because it's easier to get a better idea of what a file might be if you know its file name. And Git doesn't tell you its file name at the blob level, it tells you the tree level. And that just calls off into other functions. But what that allows you to do is you can start recursing, which is quite fun. So now when you are, for instance, you're looking at the commit message, and the commit message has something like, oh, this bug was fixed in commit 2930 or whatever, and you're like, oh, okay, well, that's going to completely change because Git history has changed and all the commit IDs have changed. And you're like, but I can just map it. I'll map it using the same function that I've got right here, and I'll update the commit message so that it reflects what the new commit ID it is. Oops. I had an example of that, but I think it's a bit out of order. So that's really fun. You can you've got a much more powerful and expressive way of like monkeying these things together. Git-filter-branch doesn't actually do this. Like, it doesn't rename your object IDs in the commit messages. It's kind of a nice to have feature, but actually it does have like some minor security implications, because there's a potential for deriving what a removed password was from the old commit ID if it was in a commit message. It's quite tricky, but I've written some proof of concepts. It can be done. Anywho, so it goes faster. And like, how much faster? And simpler to use. Yeah, so like if you wanted to remove a file, that's how you do it in git-filter-branch, and that's how you do it with a BFG. That's nicer. I'm using what's it called? There's a nice library for parsing arguments. I've completely forgotten its name now, but it's really good. You can have a look at the source code and figure it out. And so this was tested against the Google Chrome codebase, Chromium. They're trying to transition from SVN to Git, and they have a lot of bad history that they need to get rid of. And so Elliot Glacier, an engineer at Google, he tried it out. And he found that he could get the repository, which was about 20 gigabytes or something ridiculous, down to 500 megabytes in 10 minutes using the BFG. Using git-filter-branch, it would have taken 3 days. And that's quite a long time to be out of action. And not even got quite that small either. So it runs faster. Now, would anyone like to see a demonstration of it running a bit faster than filter-branch? Anyone want to see? No? Yeah, go on. Okay, I'm glad. That's enthusiasm. I like that. Right. Okay. Blah blah blah. Okay. Right. So. Okay. I'll do the BFG first. BFG. Okay, so what I'm going to do is I'm going to delete that worksheet folder that Martin should never have checked in. Now, with filter branch, I'd expect this to take a few minutes. We'll see how long it takes the BFG. That's done. So, and it's given you like some nice readouts. It sort of said, oh, your history was pretty dirty. And the worksheets files, they were up there, but after that, it's just modified history. There wasn't any more dirt after that. And so let's just compare that with git-filter-branch. Okay, so this is essentially the same command, but in git-filter-branch. Bang. So, you know, it's churning along, and that looks like quite dramatic. It's doing stuff. But it will slow down a bit. And so what it's doing that thing where it just sort of slides along the repo and does each commit, cleans it over and over again. This repo is not too big, so eventually we get there. Yeah, we're done. Okay, so that wasn't too painful, but with bigger repos it gets worse. So just have a look at what that looks like when the BFG does repo clean. I'll just animate that and you can see. So what it looks like when the BFG does it is this. You see that? Huge amounts of data were cleaned straight away. And it's able to attack the repository in parallel. It's able to use all the cores of your machine. Now, git-filter-branch isn't able to do that because you can't build a git commit until you've got all of a git commits history. And it works on a commit-by-commit basis. But the BFG is able to parallelize the action of working on the file trees because file trees don't depend on the previous commits. And so, well, it's done basically. But it's able to use all the cores of your machine in parallel using the nice parallelism features of Scala. In fact, I'll show you the amazing parallelism that it does. Where is it? Yes, look at me. I can do parallel code. This is really bad code, but it works. It just goes through the commits and it says, start cleaning those trees. Just clean all of them. And it uses the par operator to do that. And it sets that off in a future. And then for the rest of the commits, which do have to be done in sequentially because they've got history, it just starts operating on those. But in the background, those commits file trees is being cleaned on all the other cores of the machine. Oh, right, yes. This is a usability thing. The BFG treats you like a reformed alcoholic in that you've made mistakes in your past, but now you've cleaned up your act. So it won't modify your current files because it thinks you're probably sensible enough to have it right now, which is a nice usability feature because it means you don't have to be scared about annihilating your current code base. If your code currently compiles, then it's not a problem. Whatever the BFG does to you won't destroy your current code. Well, so that's nice. Oh yeah, and there's that commit message where it sort of takes the old commit message ID that was it takes the old commit ID that was in the message and it replaces it with another one. Just to demonstrate how much faster it is, I was going to do it here actually, but there's probably not enough time. Is quick demonstration using a Raspberry Pi, assuming this loads up. So over here we've got a quad-core Mac, nice one, and over there we've got a Raspberry Pi. I've actually got the Raspberry Pi here. I was going to demo with that. So it's like a $25 computer, and it's got a 700 megahertz processor. It's pretty slow. And so I pitch the two against each other. So the Raspberry Pi is running Scala, and it's got like a slightly slow startup time for the jar. And you can see that git-filter-branch has an advantage at the start. It's ahead by 800 commits or so. But Scala, running on this single-core ARM processor, starts to catch up. neck and neck. Now the BFG's in the lead. And this is sped up because it's a pretty boring video to watch, to be honest. But we end up with BFG wins. There we go. And final scores. The quad-core Mac would have taken 45 minutes. The Raspberry Pi would have taken 25 minutes. And if you actually ran the BFG on the Mac, it would just take 1 minute and 10 seconds. So it's pretty much way faster. That is pretty much all I was going to show. Does anyone have any questions? No? Let me think if there's anything else I can tell you. I think that's probably about all I've got. So if that's all, thanks very much. Oh, hey. Yeah. Well, that's an interesting. So where you're taking advantage of sort of memoization and stuff like that. That's a really good question. Well, you could do, like, for instance, searching history might be faster. Like, I think this is like a really good example of that case with filter branches behavior. I'm not sure off the top of my head what else there might be. One other project that I did do in Scala and Git is Goohoo. I don't know if you've heard of it. So there's a bit of a problem with running a big organization and using GitHub is that eventually you sort of get lost and you can't remember who all the people are in your organization. So Goohoo is like a simple play Scala app that uses Git and the GitHub API to check that all the people in your organization fulfill like basic criteria of having like two-factor authentication, having a full name, and most interestingly, it checks that they're all listed in your user's file, and that's interesting because if you ensure that everyone's listed there, you can git blame the file, and you can see who was responsible for adding the person in question. Me and Lindsay at The Guardian wrote this, and it's quite fun. And it actually, in order to work, it has to check out the Git repo. And we were able to prototype this very quickly with Scala and using JGit. And the app's up on Heroku now if you're actually willing to put your GitHub credentials into my Heroku app. So I can just quickly run that through. Yeah. So this hits the GitHub API, finds out who hasn't got two-factor auth turned on, and oh, look, there's actually someone who has got something wrong with them. And what it does is it opens up a GitHub issue against whoever those people are. So that is sometimes the only way to contact people if they don't have a like an email address against their profile. You might not know who they are, they don't have any contact details, but if you open an issue against them, they get an email. So that's how they get in contact with them. So that's another example of prototyping with Scala and Git. Oh, yeah, sorry. Oh, right, okay. So the back end of that is basically a Scala Play app, and the front end is using 3JS. So, I built this on Saturday at a hack day at the Tate Modern, where we were supposed to be creating art from data. So I was like, I'm going to visualize a Git repository. So it's using 3JS and doesn't actually use Scala.js, though I feel like after having seen some of the talks that it probably should. The Scala backend basically grabs the Git repository and chomps it down into quite a small, simple JSON format, and then that's just sort of blatted out in 3JS code. So I haven't actually open sourced that yet, but if anyone's interested, I'd be happy to lay it out. Yeah, it's lots of fun to write. Anything else? I can see a guy doing this in the back. Okay, well, thanks very much. I'm Roberto Tyley, and yeah, it was really nice presenting to you today. Cheers.